Thank you all so much for joining us today for our last RD Updates episode of 2020. And I just have a couple of quick housekeeping announcements, and then I'm going to turn it over to Beth Kitchen to introduce our guest, who we are very excited to have with us here today. But the housekeeping items, we do encourage you to ask questions throughout the session. So if you think of anything while we're going through the presentation or throughout the talk, please just type your questions into the chat box. And at a good point, I'll interject and ask the questions. We can make sure to get those questions answered while they're fresh on your mind and related to the topic we're going over. And also for any of our registered dietitians who are on the call, you can get one CPEU for attending today. I just have a quick survey for you to fill out, and then I will send you your CPEU certificate either later today or early tomorrow. So I'm going to go ahead and put that link in the chat box now. But with that, I will leave Dr. Kitchen to introduce our guest.
Thank you, Tara. This is Beth Kitchen, and I'm really excited to have with us today Dr. John Waterborne. In full disclosure, Dr. Waterborne was my epidemiology teacher when I was getting my PhD in the School of Public Health. And he left a lasting impression upon me, and I learned a whole lot from him. So that is one of the big reasons I wanted to have him on the show. He is an associate professor of epidemiology in the School of Public Health here at UAB. Over his 30-year career, he has won the UAB President's Award for Excellence in Teaching in the School of Public Health twice. And he has been a fantastic mentor for doctoral and master's students studying the prevention, causes, and early detection of cancer. He has served as the chair of the Alabama Comprehensive Cancer Control Coalition and advised the development of the Cancer Control Plan for Alabama, as well as served on the Alabama Statewide Cancer Registry. So join me in welcoming Dr. John Waterborne. Dr. Waterborne is an MD and PhD, right, John? Dr. Waterborne?
DRPH.
DRPH.
Yes.
Yeah, so welcome and thanks so much for being here. And what we're really going to focus on today is talking about nutritional epidemiology, specifically observational studies. And what we're going to do is we're going to actually talk about some things in general with Dr. Waterborne, have him enlighten us on some concepts. And then we're going to do a deep dive into just a couple of studies that have been part of the headlines. And Dr. Waterborne is actually going to show us like what parts of the statistics, the study design, we really need to zero in on, and how can we interpret these more accurately when we get these questions from patients, consumers, and the public. So Dr. Waterborne, let's start with talking about some, epidemiology, observational studies. Can you kind of define some terms for us so we all know what we're talking about? And I want to reiterate what Tara said. As you have questions, please, as you have them, put them in the chat box, because we want this to be, of course, a conversation.
Thank you, Tara and Beth, and everybody hear me okay?
Yes.
Okay. So I was invited to tell you what I know about epidemiologic methods as it applies specifically to, I guess, nutritional epidemiology. Epidemiology is, of course, the study of disease causation. There are two varieties of epi studies. We call it epi just to be brief. The so-called descriptive studies just look at rates and trends of different diseases in different populations, either geographic populations or racial and ethnic groups, that sort of thing. When you talk about analytical epidemiology, then that's where the payoff is, causation. That is, we want to know what causes diseases and what maybe makes diseases more common or less common as time goes on. And the reason for that is that in public health, my main area, what we want to do is, as time goes on, prevention. So if you're a true public health professional, which I don't know how professional I am, but I guess that's the field I'm in, you mostly deal with well people, not sick people. So what we want to know is what's the causes of lung cancer, what are the causes of cardiovascular disease, so on and so forth, so that we can prevent the next case. I think that's really where we're at. In terms of the literature and studies that are published, Again, it's much easier to critique a study or two, like we'll do a little bit later in a half hour or so. It's much easier to critique it than do a good study oneself. What I was taught to do was, number one, look at epidemiology primarily as something rooted in clinical medicine. By clinical, I mean patients, nutritionists, psychologists, anyone who sees patients who, by their history of their particular disease, give clues as to why they got the disease of interest. So a lot of people, this is my little preamble, a lot of people equate epidemiology and biostatistics. I would say no, two different things. Biostatistics, I would say, is not even a root of epidemiology. It is a tool that we use for one part of our analysis, which is basically to exclude the possibility of chance findings. Chance findings would be findings that you see in terms of rates and trends that could be due to nothing that could be identified as an exposure or a cause, just kind of random events. So don't mean to trivialize statistics, maybe quite that much, but the idea is, I think, before you can conclude cause and effect, you should have some biological evidence in addition to some numbers.
So John, that sort of leads us into what we're talking about today, which is Hill's criteria. So if you want to go forward with your slides.
Yes.
Let's sort of talk about, some of the, you basically sort of just went over this, that the purpose is to look at causation. But that's tricky. And so one of the things I wanted to ask you to do is sort of talk about the difference. We say epidemiologic, I use the term observational to talk about a lot of studies. So let's talk about some of these differences here.
Okay. So studies, so-called etiologic studies, etiologic means causation, are generally done in an observational mode. The two big observational study designs in EPI are follow-up studies, also known as cohort studies, and case control studies. The other general type of study design is experimental. And experimental is quite different. Experimental means you, the investigator, controls the exposures and assigns exposures, like half the people get one exposure such as a drug or a particular diet. The other half do not get that exposure. That's a generally tighter study design because experimentally what you're doing is trying to look at two groups that are quite the same as one another, other than for one factor, that one group has a different diet than the other or a different activity than the other. You, the investigator, control the exposure. That's an experiment, as you would do experiments on animal research and in other situations. Observational studies are, though, usually what we're confronted with for epidemiology. And that's because a lot of the exposures, and exposure we use here as a noun, an exposure can mean a lifestyle habit like smoking or drinking. It could be an environmental exposure like pollution. Usually in epidemiology, we're studying the effect of exposures that are harmful, or so we suspect. We cannot ethically randomize people to half of you smoke cigarettes and the other half don't, or that sort of thing. So we're reduced to observational studies, which mean we simply find people who have an exposure that we think is harmful, and we find demographically similar people that don't have that exposure, and we study them to see which group has a higher rate of disease. And sometimes there is no difference, but what we're usually looking for is whether the group that's exposed to, for instance, environmental pollution, do they have a higher rate of cancer than those who are not exposed? Why the observational study designs are weaker is something called confounding. Confounding is what we try to avoid when we do an experimental study. Confounding means the influence of an exposure other than the one you're focusing on that actually may be the reason for the disease. So for instance, if you do a study of cigarette smoking and you find that smokers have a higher rate of disease than non-smokers, Is it in fact because of the smoking? That's possible. Or is it because smokers systematically do something else compared to non-smokers that could cause the disease? So if it's true that most smokers drink alcohol and most non-smokers don't, you could be fooled into thinking that smoking is the cause because there is confounding by alcohol. So sometimes the exposure you focus on is not the real cause, it's a correlate of that exposure. So to get to Hill's criteria, Sir Austin Bradford Hill, back in 1965, which seems not all that far back to me, but I guess to other people it is. For the Royal Society of Medicine, Sir Austin Bradford Hill proposed a set of hoops to jump through that are called Hill's criteria for causation. And Hill's criteria are something we want to look at before we conclude cause and effect. So before you get to cause and effect on my purpose slide, when you do an epidemiologic study, as I have done, and several of you out there have done, we need to get away from the idea of proving your hypothesis. A hypothesis means when you do a study or plan a study, you have to have a particular target or a particular focus. For instance, does a high-fat diet cause breast cancer? You can't do a very general study without with any success. You need to focus on a particular exposure and a particular disease outcome. Before you ever get to causation, you look for statistical association. That is, in the lung cancer smoking example, let's say we didn't know what the answer was, is there an association between smoking cigarettes or heavy smoking and lung cancer? Association means that's a statistical term. That means, in this example, do non-smokers have a higher rate of lung cancer? It's usually the non-smokers. That's what we mean by association. There are three, in paragraph or part 2 there are three explanations in general for association. One of them is causal, or cause and effect. We come to that last. Number 2 is a so-called indirect association. That's what we mean by confounding, that you're focusing on cigarette smoking, but that's not the cause. The cause is something else that cigarette smokers do that the non-smokers don't do. The third explanation, which comes up now and then, is the spurious association, meaning there's no rhyme or reason. You might get a spurious association in a small study, and if you repeated that study, it wouldn't come up again. Anyway, that's what we're aiming at. We want to find out causes, but we don't prematurely want to conclude causation until we eliminate other explanations for our association.
So then these are all the other things, right, John? These are all the things that it could be.
What Dr. Kitchen mentioned, yes. Chance or small sample size could be the explanation for an association that you find in your data. Chance is more likely a cause in a very small study. The effect of small numbers or randomization, random chance. Beyond that, another thing you want to look at is confounding, what I just mentioned. There is a correlate, which means it could be, another exposure experienced by the people you're studying. That's the real explanation. Something we didn't mention yet is bias. Bias, not the same as the dictionary term that we use today when certain people don't like certain groups of people, that sort of thing. Bias here is an epidemiological definition, systematic error. There are two types of bias, two classifications that they are called selection bias and information bias. Selection bias means the people you are studying were not representative of the people you were trying to study. Information bias, we'll come back to that later, means there is a systematic error in how you collected data from one of the two groups you were studying. Usually, again, you need two groups to conclude causation to have any hope of that, because you need to have a comparison group to compare exposures or disease rates with the group of primary study.
John, I want to ask you a real quick question here. I want to go back to confounding for just a second before we move on.
Okay.
So when we talk about confounding, and there are all these other things besides, we're studying, say, smoking and lung cancer. And of course, it could be other things. Maybe they drink more, maybe their diet is worse, all these other things.
Correct.
Talk just a little bit about controlling for those variables. And, basically, does that completely eliminate confounding, or what can we say about it, controlling for those variables?
Okay, great question. So confounding, again, is a major issue in observational design, such as the follow-up or case control. Two ways to control for confounders. Number one is called, in the design phase, designing your study, called subject characteristic restriction, a little bit of a mouthful. So if you wanted to do a smoking and lung cancer study and you were concerned about confounding by alcohol, what you could do is study only smokers and non-smokers, none of whom drink alcohol. That is, you could select your subjects, none of whom are exposed to that potential confounding factor. Now, so you wouldn't have any confounding by alcohol if nobody in the study drinks. The limitation there is you're not sure whatever results you get, would those results apply to smokers who do drink alcohol? So that's a limitation in the design phase. The other way to control for confounding, which is more common, is in the analytical phase. That's called standardization or adjustment. So what you would do to control for known suspected confounders, you may not know all of them. When you do your study, you read up on the disease of interest, like lung cancer. I happen to know there's a contribution to causation, like alcohol drinking is part of it. Another cause of lung cancer is radon exposure. Radon's a radioactive gas in the earth. Another one is asbestos of certain types. There are other occupational exposures but let's say again, your goal is to look at smoking in lung cancer. You must anticipate possible confounders in your data. This is before you do the study, before you start collecting your data, and make sure you collect data on these known, be phrased as known or suspected confounders. So even though my goal is to get a detailed smoking history, I'd want to know, for each subject, are you exposed to asbestos? What is your occupational history? Do you live in an area or a county where there's a radon exposure? What I would do then is, only if I've collected those data or I can't do anything about it in the analysis, I would adjust my relative risk estimates for these confounders. I would adjust for radon exposure, adjust for occupational exposures, adjust for asbestos, and then I would have an adjusted relative risk. The relative risk is the main variable we use to say how many times bigger or smaller is the rate of disease in the one group versus the other. So for instance, if I did a smoking and lung cancer study, maybe my so-called crude, C-R-U-D-E, my crude or unadjusted relative risk might be 10. When I adjust for my confounders, that changes the relative risk point estimate. I'll make up a number, changes it down to 7. That means 3 points of the high relative risk were due to these confounding variables, which I didn't want to study, but I did want to take note of them so I could have them wash out of my data and then come up with an adjusted relative risk that reflected only the influence of the smoking.
But just doing that doesn't then mean and we're going to get to this, but I just want to point out that just because you've done that doesn't then mean you can say, well, it must be causation.
True. All it says is we've done our best in that area of.
Right. And we're going to talk about that a little bit more when we get to health criteria. So yeah.
So as important, chance and confounding are both, well, confounding is both a validity and precision issue. Bias, and then we'll go to the next slide. Okay, big picture of this slide. There are two main categories of importance in epidemiology. They are validity and precision. Validity is lack of bias. Bias has nothing to do with the sample size, nothing to do with numbers. Bias is determined by how you choose your subjects for study and how you get information from them in a neutral fashion. So bias is actually the more important aspect of a study. Secondary is precision. Precision is how many people did you study, your p-values and that sort of thing. And we'll get to that second. Anyway, to wrap up this slide, you conclude causation. I consider that my conclusion of last resort. Once you're done your study, you look at your data and you say to yourself, number one, could chance be the explanation for my study? And real quickly, you would say, no, I did a really big study. So I don't think that's the answer for my explanation for my results. Confounding, is that the explanation for my study results? I would then say, well, did I collect data on known and suspected confounders, and did I control in my adjustment procedure, which is a mathematical procedure? Yes, I controlled for confounders. Number three, bias. Looking back, my study's already done now. Did I select my people appropriately to study? Did I get information from them, maybe on their diet, in a neutral fashion, treating each group, the index series, the people I was mainly interested in, maybe they ate the high-fat diet, and the comparison group, was I neutral and level on how I got information from those two groups? Yes, I think I did a great job, no bias. Then you start thinking, maybe you have cause and effect. So that's what we say here. Sir Austin Bradford Hill, 1965, gave an address to the Royal Society of Medicine in the UK. And he gave an address that went down in history in epidemiology on what is known as Hill's criteria for causation. 50 years later, in the year 2015, not too many years ago, his paper was reprinted in the Journal of Occupational Medicine. And I haven't done it yet. I can email Dr. Kitchen that reprinted paper. And Dr. Hill went over what I call them 9 hoops criteria that you should use in looking at your data to see if, in fact, you have hit upon a cause of the disease. Now, no need to look at those criteria for causation until you have first considered, where my cursor is, imprecision or small sample size, confounding, and bias. So again, if you have a relative risk above 1, relative risk of 1 is the null value, meaning no association. If you do have a statistical association, like smoking seems to go along with lung cancer, and if you have eliminated imprecision, confounding, and bias, then you start thinking of, maybe I have a real cause. Now let's see if our data stand up to many, probably not all, many of these hoops. So number 1 is strength of association. That means how big is your relative risk? So in lots of epi studies today, we find a relative risk of 2 or 3, something in that neighborhood, not like a 10 or a 20, other than for smoking and lung cancer. The higher the relative risk is beyond the null value of 1, the more convincing it is. Like, could you make enough errors in your study to give you a relative risk of like 5 or 10? That's hard to explain in terms of errors or biases. You must have written really poor study. But that's only one thing to look at. Number 2 is dose response or biological gradient. Again, not absolutely necessary, but the thought there is, for instance, smoking and lung cancer. If smoking or tobacco use causes lung cancer, it might make sense, at least to many people, that the people who smoked more would have an even higher rate of lung cancer than the people who smoked a moderate amount, and they in turn would have a higher rate of lung cancer than the people who smoked only lightly, who would in turn have a higher rate of lung cancer than the non-smokers. So we look for in our data, we look for so-called dose response or biological gradient. Does more of a bad thing cause even more disease? Now, again, my caveat there is that in some situations, maybe there is not dose response, but there is cause and effect. One explanation might be radiation of certain types, that up to a certain limit, up to a certain threshold, a little radiation dose, maybe sun exposure. Doesn't matter, let's say, doesn't cause any malignant melanoma. And then after a certain point, whammo, that's enough radiation to cause a skin cancer. So the idea there of dose response is, even if it isn't there, it doesn't mean you don't have cause and effect, because there could be a threshold situation.
So it might not be linear. We talk about this with like
Correct.
fish and PCBs. Like there's a lot of controversy over whether PCBs cause cancer. And some people think, you know, a little bit, there's no, maybe this is the idea that it has to get to the threshold before you see any. So it's not going to be linear. You're going to see no effect, but then boom, when you get here, that's where the risk starts, is at this threshold.
Correct. And Dr. Hill recognized that. Although, again, in several epi studies that I've been involved in, there is a dose response. But anyway, if you do find dose response evidence in your data, that's another check mark, another box checked off, like maybe we have cause and effect here. Number 3, consistency. Because the epidemiologic studies are usually observational, meaning there's the potential for confounding. It's not as tight a study design as a randomized controlled trial. We look for consistency. So even if I do an epi study that I'm convinced, I think we got cause and effect here, I don't run to CNN or the New York Times or to Dr. Kitchen for her television address. I don't claim anything really until other investigators, as competent or more competent, hopefully, than I, unrelated to me, not in my own research group, can these results be reproduced? Again, not exactly, because someone at another university wouldn't have the same subjects in their study and things might be done a little differently. Does the same result essentially keep popping up? If that's true, again, another checkbox, maybe we have cause and effect. Number 4, temporal relationship. Temporal meaning time. For an exposure to cause a disease, the exposure, this seems like a duh, the exposure has to happen first. Now, we say this because in some study designs, one study design we didn't mention is the cross-sectional study, also known as a prevalence study. That did come up in one of the articles we're going to look at. In some study designs, it is not clear that, for instance, did the smoking happen well before the lung cancer was diagnosed, or did the smoking happen later, or even not much before? That is, to digress a bit, for every disease, chronic diseases, there is an induction period. Induction period is the length of time between exposure to something and the disease that it causes. So for smoking and lung cancer, the induction period is on the order of a high number of years, 10 years, 20 years. So nobody think, I'm a non-smoker right now, nobody thinks if I smoke nobody thinks if I smoke cigarettes this week, I'm going to get lung cancer next week. Doesn't work that way. There's an induction period of 10 years. So the point is, when you do a smoking and lung cancer study, if you're going to blame smoking for the lung cancer cases you see, can you document that the smoking preceded the diagnosis of the disease by 10 or more years? So that's, again, temporal relationship. Specificity. This doesn't happen much. There is an interesting example. Specificity means if there is an unusual disease restricted to an unusual group of people, that's going to be hard to explain other than cause and effect. So the example there was in the early 1900s, there were chimneys and chimney sweeps in England, in the UK. And the chimney sweeps were usually young men or boys who were very skinny, we might say, and they would lower themselves into the chimneys and sweep out the soot. These chimney sweeps came up with an unusual cancer, cancer of the scrotum, of course, exclusively male cancer, and an odd group because these were young boys, and young boys usually don't get cancer of anything. So Sir Percival Pott, P-O-T-T, found that, and this is maybe one of the few examples, but it's very telling. Scrotal cancer cases were diagnosed. These were all young boys. I'm thinking of, 12-year-olds, 14-year-olds. when these boys are interviewed, what do you guys have in common? Hey, we're all chimney sweeps. So specificity, which doesn't happen much, says this is a big checkbox to check off. How it would relate is if there's an odd leukemia out there today in the United States or elsewhere, and if all the cases of that odd leukemia worked in a certain sort of industry, then that's pretty telling. And like no cases did not work in that industry, that might be pretty telling or pretty suggestive of cause and effect, because nobody else gets this unless you worked in occupation X. Biological plausibility. Again, epidemiology is rooted, I think, in clinical medicine and biochemistry, physiology. Can a case be made by, let's say, a biologist or a physician, biologist, epidemiologist? Is there something that says, yeah, this could work? For instance, smoking and lung cancer, we know certain chemicals in smoke, there's some animal studies, et cetera, et cetera. Coherence. Is your new finding of a supposed cause, does this fly in the face of previous knowledge of this disease, or does it kind of fit right in? If it fits right in, we have another box to check off. If it somehow violates things that we understood or thought we understood before, then maybe we need to look at this more closely. Experimental evidence, usually not available, because again, an experiment would mean, an experiment of smoking and lung cancer would mean, which I can't do this ethically, find a bunch of non-smokers, randomize them to the smoking group or the non-smoking group, follow them for 20 years and see who gets more lung cancer. So usually, and it's acknowledged even back in 1965, that experimental evidence is usually not available. But if you had it from, I don't know, a prison population when it was things were done which are not ethical today, or some other country, and experimental evidence is pretty, again, solid. Analogy, that's another thing to look at. So if you're looking at a leukemia caused by a certain chemical, maybe this leukemia was not seen before. Analogy means, is there a similar chemical of a similar chemical structure that causes some other sort of leukemia? So can your relationship that you're looking at now, is there some similar exposure that causes a disease similar to the one that you think you're looking at now? So the idea of Hill's criteria is, and a few of these involve numbers, but mostly kind of not. Hill's criteria are something you look at when you have an association in your data, a relative risk well above 1. You can't explain it away by it's a small study. You can't explain it away by confounding, because you controlled for confounders, or so you think. And you can't explain away the association by bias, because you think you were a straight shooter and did the study very well. And again, treating each study group the same. Questions on that, Dr. Kitchen, or comments?
So obviously they don't have to fulfill all of those. They've got to fulfill at least a chunk of them. I'm guessing that means what, 4 to 5? Is there a set number of criteria?
I think Dr. Hill said, again, the 1965 paper, which I will email you, and then you can pass them on.
Yeah, sure. It's a great paper.
I think he says the majority. I mean, in some particular studies, and one or more of these, like experimental evidence, may not.
Yeah, that's not going to happen. Yeah.
If you're the first study ever done of a certain disease, the majority. So again, right. What I have done with
maybe more like 7 or 6, 7, 8 we're looking at.
Yes.
Yeah. So what we're going to talk about now, and if anybody has any questions at this point, let us know. We're going to look at a few studies that were in the headlines, that the headline suggested causation. This one, avoiding ultra-processed foods may increase lifespan. We're going to take a look at this study. When I see words like increase, even though they put may in front of it, I go, if it's an observational study, even saying may increase, I feel like it should say may be correlated, because it could be a spurious correlation.
Yes.
So so this is the first study that we're going to look at. And so let's take a look at let's do headline versus study now. So that was the headline. And then here's the actual study.
Yes. So again, importance, growing evidence, which I can't vouch for because nutrition is not probably my strength. My strength is maybe epi methods. Nutritional
You know the
epidemiology, I know,
methods
is
here.
very
You can talk
challenging.
about the methods. Yeah.
Growing evidence indicates higher intake of ultra-processed foods. I take that as a given because you couldn't prove it by me. Higher incidence of non-communicable diseases. That's a very broad statement. I mean, I don't know anything other than maybe radiation that in excess can cause a disease of any part of your body and kind of anything. Anyway, I'll go on. Ultra processed foods. Okay, I've heard of them, but so the objective assess the association. Foods consumption all cause mortality risk. Okay, we'll go on to on. These are again for the study from the study itself. I have a few slides of things that I don't like about what words are used and how things are phrased.
Okay.
Observational study, and the study group is well defined here from a French study that again there is a cohort study, and these investigators were able to use subjects from that study.
So we're going to compare this to Hill's, right? We're going to go
Yes,
look at does it fulfills Hill's criteria for
right.
causation?
Ultra processed foods. Okay. So main outcomes and measures. Overall mortality was the main outcome. And skip read, I don't want to read it to you. Hazard ratios were calculated. That's a relative risk per increment of dose, like per increment of bad diet, for instance. A lot of numbers here. And the results, part of these are not results, they're kind of who was studied. Men and women, they looked at what I thought was odd, but I don't do nutritional epi studies myself, proportion of the diet devoted to ultra-processed foods. Conclusions, an increase in ultra-processed foods appears to be associated with overall higher mortality risk. Okay. And this was modeling. So
let's go back to that modeling slide right there.
yes.
Yeah. So when, as dietitians, this is what we need to look at, right? Because you talked about this is how we control for the confounding.
Exactly. So here in confounders, so a model is basically an equation. On one side is the outcome, and the other side of the equal sign are the so-called risk factors, or factors that you think are important, such as dietary content, smoking, whatever. And what you do is in a model, try to find coefficients for how important each of the explanatory factors happen to be. So a high coefficient would be a multiplier of 5 or 10. A low coefficient would mean it's less important. So what you find here is model number 1, which they described, is significant. The p-value less than 0.001. Models 2 and 3, and I make a comment in my slides there that I made up myself. When you go from model 1 to model 2, the hazard ratio doesn't change much. So what that means is model 1 adjusted for sex and age, and that's, let's say, the go-to model. When we go to model, and this is sometimes done, when you go to a second model, you say, I adjust for everything I already adjusted for, plus I'm going to adjust for all these other things, and that's a bunch of things. This number didn't change much from this number. And then when you go to model 3, adjust for even more things, changes again very little. So these numbers are pretty much the same. So what it means is the adjusting for sex and age makes a difference. Adjusting for these other variables, not so much.
Okay. And so now we're going to talk about how you felt about this with Hill's criteria.
Yes, I think maybe I'm on, let's see, am I on the wrong slideshow? Because I don't have,
I think,
I want to be on my edited one.
yeah, do you want to pull that up?
Yes, I thought I had it up already,
I thought
sorry.
you did too. Yeah, yeah.
So where did it go? Sorry, folks. No, this gets into the other study.
Yeah, if you want to pull that up, we can
Yes, I
keep
will.
talking. So, and yeah, Angela is saying, can we find these slides? Yes, we can share these slides with you. And so is everybody on board with what Dr. Waterborne was looking at with, looking at the p-values? So the p-value is what tells you if it was significant. And then he looks at how the adjusting affected the relationship. So you always look at the different models. And what you should always report, even if it's not that much different, you should always talk about the adjusted models, meaning they corrected for those possible confounders. And the other thing that Dr. Waterborne is going to talk to us about is how important these confidence intervals are in the parentheses, because, we can say, well, it was statistically significant, but we have to look at these confidence intervals too. And that's the thing that Dr. Waterborne is also going to touch on here.
Yeah, p-values, I usually, just momentarily now, I'm on the right slideshow.
There we go.
Yeah, I don't know what happened before I had it up.
Yeah, it was weird. We had them up before.
A p-value, p means probability. A p-value means, are your results consistent with the null hypothesis? What's the null hypothesis? The null hypothesis means the exposure you're looking at, such as ultra-processed foods, has no impact whatsoever. You might as well be looking at, sugar pills or something else. What you want to do in, you can calculate a p-value, although again, Ken Rothman, who's a leading epidemiologist and former editor of the journal Epidemiology, he did not allow anyone to publish studies in his journal that use p-values. He said, I want confidence intervals, and that's it. So here they have both, so I'll just pause there. So things are highly significant. When p-values are very small, it means you could, again, there's no absolutes. P-value is very small, like less than 0.001, means you couldn't possibly have gotten these results by chance. By chance means ultra-processed foods has no impact at all. Could you have gotten these results if that's true? If the p-value is low, they would say no. No way could you find this association of 1.20 because the study is so big. So p-value is consistency with the null. So in the p-value, the usual cutoff we use is an alpha level of 0.05. If the p-value is very low, anything less than 0.05, we would say, well, very unusual, almost impossible, you would get this by chance. Therefore, probably you did not get this result by chance. You got it because there was an effect of, again, the ultra-processed food diet. So the p-values and diminishingly small, the limitation, and again, in this study, that it's a good thing, they publish both confidence intervals and p-values. In studies that only publish p-values, that doesn't tell you the plus and minus of your, what we call the point estimate. The hazard ratio for model 1 is 1.20. That's the point estimate. Our single best, this is a variety of relative risk. Single best number expressing the relative risk between ultra-processed food in the diet and mortality. The confidence interval is built by a mathematical formula around the point estimate. So you take the appropriate formula and it's the hazard ratio minus or plus some number. Here's what this confidence interval turned out to be. So you would say this answer is statistically significant because the confidence interval lower limit does not include 1 and it's not a number less than 1. So what you'd be saying here is in model number 1, the best hazard ratio relative risk is 1.20. That is 20% above the null. So 20% of the mortality is the endpoint here, above what was expected, 20% extra is due to, if you can include causation, the ultra-processed food diet, but your sample size is such that 20%, that is 0.20 above 1, is our best estimate, but it could be as little as 8% or 32% above. So confidence intervals and p-values do correlate somewhat. You can kind of calculate, if you have enough information, one out of the other. If you only had the less than 0.001 p-value and no confidence interval, you wouldn't know how stable the 1.20 estimate is. So in epidemiology, we often do confidence intervals and not worry about p-values, just do that. But that's kind of a matter of, are you a statistician or an epidemiologist, and your kind of your point of view thing. Okay.
But John, let's talk, can you, that's really great information. But so the reason that we really need to look at the confidence intervals is that the 1.2 is a point estimate in this study. If we did a similar study many, many times over, what the confidence interval is telling us that could be in reality anywhere from an 8% relative hazard ratio or relative risk up to a 32%. Is that correct? Did I say that right?
Exactly. You're a great student, Beth.
I learned from the best, John. I learned from the best.
Gosh,
So
Mutual Admiration Society.
Yeah. In other words, this is one study, but what this is saying is that if we did the study over and over again, which we never make a recommendation off of one study, it could be as low as 8%. So this is 20%, could be as low as 8%, but also could be as high as 32% or somewhere in between.
Yes, because to rephrase and add on, the 1.20 based on, it's a big study, but it is what it is. It is, if we did a valid study, it is a good estimate of the so-called population parameter. Population parameter means we never know the answer. If we knew the answer, that is, population parameter would be a study of unlimited size of this nature. What you're doing, let's say you, as Beth mentioned, let's say you did have the time and the money to repeat this entire study, you would take samples of the same size, but it would be a different group of people in each sample. You would get a second point estimate. Maybe the next time you did the study, you'd get 1.27. Maybe the next time you did it, you get 1.16. Maybe the next time you did whatever. What you're saying is we only have time to do the study once. This is a 95% confidence interval, meaning that our best estimate is 1.20. And with 95% assurance, not 100% assurance, with 95% assurance, we believe the population parameter is between 1.08 and 1.32.
Very good. Okay, that's really helpful. That's really helpful.
The 1.20 is what it is. That's what you got in this study.
Right.
It is not the population parameter because you didn't study quite a big enough sample.
And what they reported was the 1.14, since that was the most adjusted model. So a little bit different, not significant. But if you looked in the media reports, what they reported was a 14% increase.
Yeah, and that's fine.
Yeah. So let's move on with talking about, does this study fulfill Hill's criteria? And that's what you're going to talk about next.
Well, yes, I guess we don't have, and tell me if I'm going on too long, which maybe I am. 2 slides, and then we'll go back to Hill's overall concern. Ken Rothman, who I mentioned, editor of the journal Epidemiology, one of our leading contemporary epidemiologists, he would call this risk factor epidemiology. Like the authors, this paper is replete with confidence intervals and numbers like all over the place, et cetera. Seems to be risk factor epidemiology, meaning looking for correlations. A point of concern, risk of mortality. This phrase is, this is again my being picky, risk of mortality, REN. We all have 100% risk of mortality. Risk means probability of some outcome. When you mention risk, you have to put a time period. So I could tell you your 5-year risk of mortality, depending upon how old you are and how sick you are. Your risk of mortality is 100%. So I think the title of the study should say mortality rate. Rate means how quickly do people die. So everyone listening to this call, we will die at a fast rate or a slow rate, depending upon how young we are and how healthy we are. Design. A flaw is when you want to demonstrate or look at possible cause and effect, not ideal to study mortality as an endpoint because mortality goes way beyond incidence. Incidence means occurrence of new cases. That's the closest thing to the cause. So if I am diagnosed today with lung cancer, I would be a good person to put in an etiologic study of cancer. If you wait till I die from my lung cancer 10 years later, this muddies the water. I mean, why did I die from it, whereas somebody else didn't die from it? This gets into health services access and all that. You don't want to study that. So you shouldn't be studying dead cases. You should be studying incident cases. Subjects, a weakness, self-reported data. Could be selection bias. So can you, whatever numbers we just discussed on the last slide, can you generalize it to people that were not in the Nutranet study? Those were volunteers. There's something called selection bias there. It may be a valid result, the 1.14 to the people studied, but this was not a study of across the population. I thought it odd, the exposures again seemed to focus, be the focus of the study rather than the outcome. Anyway, maybe that was the outcome, the extent of exposure. They looked at proportion. I would not have, and maybe there's good reason that I don't understand. I wouldn't look at proportion of a diet in ultra-processed foods. I would look at ultra-processed foods, number of servings, number of grams. Then we could calculate dose response.
And you know, John, that's one of the things that I found really interesting about this is one of the conclusions was that for every 10% of the diet that was coming from processed foods, your risk went up 14%. And I'm like, does this really show that? Because they didn't look at it. And that's what I always find really interesting about this. So people might think, well, if I eat 20%, then my risk is going to go up to 28% risk. You know what I mean?
Yes.
And I'm like, wow, how can you, when I looked at that, and that's what they say for every 10%, it's like, but you didn't look at that,
Yes, an inference that a lot of people would make. And that's, I'll come to
I looked at that and said, I don't think you can infer that, but they did.
And related to that, Dr. Kitchen, my bullet number is that 5, real 10% increase in proportion. That gets back to our previous discussion about of yesterday of relative risk and absolute risk. Is it 10% of a big number increase or 10% of a small number or anywhere in between? Anyway, table 1, p-values are going to be significant when you have big numbers. It doesn't mean clinical significance.
Mm-hmm.
So I use the explanation in class. Sometimes I'm teaching epi methods. If you have two groups of people, two big groups, and their average systolic blood pressure differs by a couple of millimeters of mercury. There's 124 in one group, 122 average systolic in the other group. That difference may be statistically significant, very small p-value because the numbers of people are so big. Differing from clinical significance, which means if your systolic blood pressure is 124 versus 122, I don't think any clinician makes any discrimination about that.
Mm-hmm.
Limitations. I don't know why they didn't do this. Again, if I did this study, I would have done, the authors say, they do mention like, oh, by the way, of our deaths, 219 were cancer, 34 were cardiovascular disease. You can't die of all-cause mortality. So in this study, if there are elevated mortality rates for certain diseases, I would like to know which diseases. And had they collected data in number of servings that could be translated into grams, however that's done,
Mm-hmm.
I would have looked at dose response and looked at 219 cancer deaths. Seems like a substantial, raw number.
Yeah.
Fairly less. They chose to look at only overall or all cause deaths. I can't imagine that ultra processed food, some of the deaths may have been from traffic crashes or whatever. I can't imagine that ultra processed foods affects and raises the risk of death from any and all causes. So I would have looked at that. Limitations, temporal relationship. They even point that out, may not be there. Okay, so let's go back to Hills. Strength of association. The 1.14, again, maybe in the realm of dietary and nutrition studies. I don't know if Dr. Kitchen or you other dietitian nutritionists think that's big. I would think that's pretty small.
I think of it as being very small.
Okay.
I teach that you've seen my slide on that I teach that it's like moderate is like at a 0.5 or a 50%.
I agree. 50% increase in risk, I would think, is something I want to know about.
I consider that moderate, not big, but I consider that moderate.
So the 1.14 statistically significant based on a whole ton of people.
Right.
Okay. So I would say no to number one. Biological gradient, I don't think they did that. Well, they did the proportion thing kind of throws me because I would look at absolute consumption. Right. There is a proportion of ultra processed foods in everybody's diet, and the complementary proportion, I'm not sure where to go with that. So I would say no answer to number two. I don't know if this has been studied before about reproducibility. I would like to see it reproduced. Mm-hmm. Temporal relationship, they admit, state. Again, looking at someone's diet after they were, after the fact, kind of, when did they change to this diet? Is it after they started to feel sick and then they eventually died? That would be counter to temporal relationship, so that's iffy. Specificity, again, they seem to think, if one read that paper, they don't say we just found ultra-processed foods causes death from cancer. They say kind of all-cause mortality, which I can't believe that's true. It may cause mortality from cancer or mortality from heart disease or diabetes. I don't know. So I don't see specificity. Biological plausibility, I will defer to Beth and others. I read the intro about food preservatives and ready to eat. And again, I'm not an expert on that. Maybe there's biological plausibility. Now, dose is important there. I think if I eat one TV dinner a month, preserved however it's preserved, I'm not sure that's going to do much. Coherence, does it fit into previous exposure disease? Here, the outcome, though, is death from anything. So again, kind of nebulous. Experimental evidence. I don't think it's analogy. So none of these am I too convinced. What does Dr. Kitchen think on 1 through 9?
I agree with you. Yeah, and that's the reason I wanted to discuss this study and others like it, because we see a lot of these. I would not say that all studies in nutrition are weak, but we see a lot of these. And so that's why I wanted to talk about this, because then we see that suggestive causal language. And I think it's our job as nutritionists. We're not promoting, I'm not saying that, processed foods are fine by any, they're good for you. But on the other hand, as we've talked about, what if studies down the road that are better designed say, no, they're really not going to increase your risk of death? And then we lose the confidence of the public when we don't report things accurately. So, and then I think the ability for us to be able to pick up a study and look at those confidence intervals, realize that that's a more important thing to look at than the p-value, and then also being able to look at hazard ratios and relative risks and understand that might sound big to the public, a 14% or a 20% increased risk. That sounds big, but is it?
Yeah, there's a plus minus to it, and it's not always translating in this particular headline. Did the reverse. Number one, lifespan is not the right.
That's what I thought was interesting about that too, because it looked at increased mortality, not increased lifespan.
Yeah.
So they kind of reversed that. It's just so crazy. And again, I'm not saying that we should promote eating ultra processed foods, but we need to be accurate. What kinds of questions do people have? Angela, thank you for your comment that she really appreciates a clear explanation. One of the things that we can do is, if there are other types that we kind of focused in on, like p-values, hazard ratio, / relative risks, and then also confidence intervals. And I think it's really helpful to kind of drill down and focus on some of these. So if you guys have ideas about other types of statistics that you would like to see, we can do that. But I think this was really helpful. Tara, do you have any questions for Dr. Waterborne? Any other questions, comments, things that you guys would like to see out there in statistics, being able to pick apart some of these studies?
I just have a comment if anyone wants to think of questions as well. I'm giving my comment if you have any. But I think that this is so helpful to see because we aren't traditionally trained with Hill's criteria for looking at studies. And the p-value, I do think, is overutilized in a lot of the research that we see that, if it has a p-value that indicates significance, that means it's a strong relationship, and that's something we should take and run with. And looking at the confidence intervals, and you see that, yes, there might be a 14% increase, but if you look at the lower number, it's a 4% increase. And am I really going to go change my lifestyle for a 4% increase or recommend to my patients make a major change to their lifestyle? Probably not for that 4%. So I think this is really helpful to see all of the criteria and what we should really be looking at for how the study is put together. Is it a good design? Can we rely on these results? And then those confidence intervals for looking at the actual statistics instead of,
very good. And
p-values.
The slide I'm on now, the p-value addresses number 1, not number 2, not number 3, and not number 4. Regardless of what your p-value is, it does address a possible reason for the study outcome, chance. P-values, confidence intervals, that has to do with precision. A p-value, big or small, has nothing to do with confounding. Did you collect data on confounders and did you adjust for them? Has nothing to do with bias. How did you choose your subjects and how did you get information from them? And it has nothing to do with causation. Is there biological gradient, biological plausibility, dose response, temporal relationship, et cetera? So the p-value, which again, confidence interval in the same category, but a confidence interval is better. They address only aspect number 1, chance, not confounding, bias, or causation.
And then, John, also, like the bigger the confidence interval, the less precise the study.
Correct.
Is that correct? Yeah. And so, and I always talk about, that 1.04, that's kind of, as I call it, flirting with null, flirting with no association. So, the bigger that confidence interval is, the less confidence you can have in the relationship.
Yes, a big confidence interval, big is bad here. And related to what Beth just mentioned, and again, the 95% is kind of a reasonable confidence interval. Shouldn't be taken as fact. That is, it's a probabilistic thing. Like 95% confidence interval corresponds to alpha value 0.05. That's the cutoff. Alpha is a cutoff, not a calculation. 0.05 as alpha is the usual cutoff for a p-value being high or low. There's no law to say 0.03 wouldn't be better, 0.07 wouldn't be better. The point is, if your lower 95% confidence limit comes, as Dr. Kitchen mentioned in this scenario, comes anywhere close to 1, that's what you need to know. Now, if the lower limit is 1.5 or higher, that's different. But rather than an absolute cutoff, you're looking for are your results compatible with no effect, the null, or are you far away from that?
Yeah. So we got those confidence intervals are what we've got to become a little bit more in tune to. Thank you. So I know we're a little bit over time here. Thank you so much. This has been really enlightening, and I'd love to have you back for more deep dives. We can talk about some other things, but I think being able to analyze, feeling confident in being able to pick up a research study and kind of knowing what to drill down on and look for. I think it was very interesting hearing you talk about the outcome measures of overall mortality was just so broad and didn't really tell us much. But these are the studies that get the big headlines. These are the studies that people talk about on websites and TV shows and all that kind of stuff. So as Tara said, we're going to be taking a break in December because it is the holiday Christmas season.
That's nice.
And we'll be picking back up in January. We'll let you know who our guest is. And thanks everybody. Tara, your closing thoughts.
Closing thoughts. Well, just to echo again of thank you, Dr. Waterborne, for coming today. This has been very helpful. I've been selfishly just taking a lot of notes the whole time. So I really appreciate the session, even for myself. And it's just very enlightening. I know, again, I've already talked about Hill's criteria and how helpful it is. And I know we dietitians know of information bias. We hear about it all the time with how are we actually getting diet related information from people and relying on recall. That's bias in itself, but it's fun to see this all packaged together as a very useful tool. So I will follow up with everyone with the slides from today so that you can have what Hill's criteria looks like. And I encourage you to practice using it on some articles and see what you come up with. And again, we'd love to have another deep dive in the future. That would be a fun session to pull into 2021. But otherwise, just if you're on the call still, if you're a registered dietitian, don't forget to fill out the survey to get your CPEU, and I'll email that to everyone later on. And thank you so much to our students who attended. I hope this was helpful to you graduate students. And we have another thank you comment to you, Dr. Waterborne, in the comments. So it's very interesting and relevant.
And anyone who has questions, welcome to contact me. And I have, from my Epi 610 Epi Methods class, I have probably 25 or so PowerPoint presentations. One's on the p-value, for instance. If anyone wants access to them, they're free. Just contact me and tell me what you want to know more about. I have one on confounding and so forth.
And take Dr. Waterborne's class if you can.